Consider a container like this and imagine making a small hole at the bottom of the container. Okay, I hope you are able to notice the hole. It's a very small hole of radius, let's say small r. Okay, now from your everyday experience, I want you to tell me, if we gently pour water into this container, suppose you start adding water in it, okay, very gently, what will happen at the hole? Quick, what do you think will happen at the hole? Fine. So the two answers I got, like both of you are saying that water will start leaking out from the hole. But actually, no. As you pour water in this container very gently, fine, what happens is you will see, water will try to leak out of the hole, obviously, but there, okay, whatever water molecules are present at the hole, they are exposed to air. So there will be a water surface present there. So if you zoom into that part, it actually looks like this. As water tries to come out from there, okay, from that hole, you will see a water surface forming here. And surface tension, okay, we had discussed this, no? The surface of water behaves like a stretched membrane. So if you think of it as a circular hole, no, fine, it's like a membrane is now present in that hole. That membrane, which is basically the liquid surface itself, water surface, will prevent water from leaking out. So as you continue adding water above, what happens is you will see a small drop forming like this. It won't leak out. Okay, water won't immediately leak out. Now, as you increase the height to which you fill water in the container, basically what will be happening, as you increase the height, you will be increasing the pressure near the hole. Okay. Pressure at the hole will be P naught plus rho g h, where h is the height to which you fill water, right? So as that pressure increases, what happens? The radius of curvature of this membrane, the free surface, decreases. So initially what will happen, like when the height of water is very less, the drop will be like this. The radius of curvature will be large. Okay. As you pour more and more water into the container, the radius of curvature decreases. Okay, it can decrease to this level, and the least it can decrease to is the radius of the hole itself. Okay, the drop hanging below the container cannot become smaller than this in radius. Fine. So you can afford to continue pouring water into this container. You can fill water in this container without the water leaking out till the drop which is hanging out becomes a perfect hemisphere. Okay, the radius cannot decrease any further. That means you can't afford to increase the pressure any further. If you increase the pressure anymore by adding some more water, surface tension will not be able to hold it, then water will start leaking out. Okay, so as some of you said, it depends on the size of the hole. Yes. Okay, so basically what happens, as you start pouring more and more water, the shape of the drop here tends to become hemispherical. Once it becomes hemispherical, that is the maximum extent up to which you can add water in the container. Beyond that, surface tension will not be able to hold. Is the idea clear to both of you? Did you understand why the liquid will not immediately start leaking out?
Yes, sir.
Okay. So now the obvious question will be, see, hole radius is given to you. Suppose liquid surface tension is T and density is rho. The question will be, up to what maximum height can you pour liquid such that it does not leak out? Okay. Try this, both of you. I'll give you 3 minutes to solve. Up to what maximum height can liquid be poured into the container such that liquid does not leak out from the hole at the bottom of the container? Okay, try. So yeah, as we have already discussed, the least radius that the drop can take is the radius of the hole itself. Okay. Now, when the radius of the drop is equal to the radius of the hole, now the liquid drop has only one surface. Outside is air, inside is water. So the excess pressure means the pressure that you can have inside the drop compared to outside. Okay. Outside pressure is P naught. The pressure inside the drop in terms of its radius will be P naught plus 2T by R, because excess pressure across one spherical surface is 2T by R. Okay. Now that extra pressure that is there inside will be built or will get built up. That pressure buildup will happen due to this liquid above the hole. Okay. So P naught plus rho GH should be equal to P naught plus 2T by R. That's all. Okay. So H is equal to 2T by rho RG. Good. Fine. Let us discuss the next phenomenon which happens due to surface tension, which is basically capillary rise. But before we get into the details of capillary rise, we first need to talk about something called contact angle between a liquid and a solid. Let's denote it by the symbol theta. Just a moment. Yeah, consider these pictures. The left side photograph is a photo of water in a glass test tube and mercury in a glass test tube. Now you observe the free surface of water and the free surface of mercury. If you observe the free surface of water, okay, it is concave to the upper side. Okay, that free surface is called meniscus. It is concave on the upper side. If you observe the meniscus in case of mercury, it is concave to the lower side. Okay, concave downwards. Okay, the right side one is a diagram which gives you a better idea. When you pour water in glass, the free surface will be concave upwards. But when you pour mercury in glass, the free surface will be concave downwards. Now, why does this happen? Why do different liquids maintain different angles of contact with glass? Okay, not just with glass, between any liquid and solid, there is something called an angle of contact. Okay, there are some factors on which it depends. Now, see, we know that there will be intermolecular attraction between liquid molecules, right? For example, suppose you consider water in glass itself. Water and water molecules will have intermolecular attraction between them. Mercury will also have intermolecular attraction between them. Okay. So that intermolecular attraction between like molecules. Like molecules means what? Molecules of the same kind. Okay. Is called cohesive force, or that phenomenon is called cohesion. The force is called cohesive force. Fine. So liquid, whatever intermolecular force they exert, that is called cohesive force. Now, when a liquid is in contact with a solid, like water with glass or mercury with glass, there will be some contact force. Okay, sorry, not contact force. There will be some attractive force between the liquid molecule and the solid also. Okay, water and glass will have a certain attraction between them. Mercury and glass also will have some attractive force between them. But mercury is of one kind, glass is of another kind. They are unlike molecules. Okay, but the force is attractive only. Fine. So that kind of attraction, intermolecular attraction between unlike molecules or molecules of different kinds, that is called adhesive force. Fine. So cohesive force basically keeps the liquid molecules together. Okay, it's the force of attraction between one liquid molecule and another one. Adhesive force is the force of attraction between liquid molecules and the solid with which the liquid is in contact. Fine. So different kinds of molecules. Okay. Now, in case of water and glass, what happens is adhesive forces are stronger than cohesive forces. What does that mean? water glass attraction is stronger than water water attraction. As a result, what happens? Water tends to spread on glass. Okay. And when that happens, so you just imagine a tangent drawn to the surface of water, okay, surface of the liquid and the surface of the solid. These two tangents have an angle between them. That angle measured from within the liquid is what you call contact angle. Okay. So in case of water and glass, the contact angle is acute. In fact, if it is pure water and glass, no, the contact angle will be almost 0 degrees. Experimentally, it has been determined. Fine. So what is contact angle? Contact angle is that angle between the tangents drawn to the free surface of the liquid and the solid with which it is in contact. And the angle has to be measured from within the liquid, not from outside. From outside, if you take, it will become obtuse angle in water glass case. That is not the angle that you are supposed to consider. Okay, by definition, contact angle has to be measured from within the liquid. So if adhesion is stronger than cohesion, contact angle will be less than 90 degrees. Okay. Now, in case of mercury and glass, what happens? Mercury attraction is very much, many times stronger than mercury glass attraction. So cohesive forces are much stronger than adhesive forces. If cohesive forces are stronger than adhesive forces, the liquid will try to stay away from the surface with which it is in contact. So it's like mercury is trying to stay away from glass. In that case, if you draw tangents to the glass surface and mercury surface, you will see that the angle between those tangents measured from within the liquid, that angle will be greater than 90 degrees. Okay. So contact angle can be less than 90, greater than 90. It can even be equal to 90. And you can guess in which case it will be equal to 90. If adhesive forces and cohesive forces are equally strong, then the contact angle will become exactly 90 degrees. Okay. Now, what happens because of this contact angle or as a result of this contact angle? Right. Observe this picture, all of you. There is some red colored liquid, okay? And that red colored liquid is common in all the tubes. Fine. At the in the bottom connector, there is this red colored liquid, and to that bottom connector, there are vertical tubes of different radii attached. Fine. And you can see that the first tube has a large radius, and in that tube, the liquid rises up to a certain level. But in the other tubes, okay, as you move to the right side, the radii of the tubes are decreasing. Okay, the radii of the liquid columns are decreasing. And you can observe that the liquid has settled to different heights in each column. Okay, the height of liquid column is different in each tube, although they are all connected to the same base. Now we had solved problems like this in case of a U-shaped tube. Fine. From everyday experience, we know that if you pour a liquid, it will settle to equal heights on both sides or in both arms. Fine. But here something contradictory or something unusual seems to be happening. Fine. Although they are all connected, liquid has not settled to the same height in all of them. It is in different heights. Okay. Now, why does this happen? This happens as a result of surface tension. Okay. Now, basically, these are narrow tubes. Okay. You can see that the liquid columns are quite narrow. So basically, we need to think of what happens when a narrow tube is inserted into a liquid container. Okay, let's consider that situation. Fine. Assume the liquid in this container and the material with which the tube is made, they have a contact angle which is less than 90 degrees. Okay, let me mention contact angle is a property shared by the liquid and the solid with which it is in contact. It doesn't depend on anything else. For water and glass, there is one contact angle. For mercury and glass, there is one contact angle. For water and plastic, there will be some contact angle. Okay. Contact angle depends on the material, liquid and the material with which the solid is made. Fine. So suppose this tube is immersed. The tube is open at both ends. Let's say we immerse it into this liquid. Okay, partially. Now, some part of the liquid will be inside the tube. The tube has a circular cross section. Okay. So inside the tube, there will be one liquid surface now. Outside the tube also there is a liquid surface. Inside there will be one liquid surface, and that surface will be in circular shape like this. Fine. Now, the contact angle between the liquid and this tube is less than 90 degrees. So if you zoom into that part where the tube is in contact with the liquid surface, okay, let's just enlarge it like this. Assume this is the tube. These are the walls of the tube. Okay. Inside there is a liquid surface and the contact angle is less than 90 degrees. So the liquid surface would be like this. It won't be perfectly flat. It will be making an angle less than 90 degrees with the tube. Okay. Now what happens? Basically, the surface is now like a bowl. We call it a meniscus. Bowl or a plate, you can say, with raised edges. Fine. So the free surface effectively looks like this. The boundary is circular, but the surface is not flat. So it actually looks like this. Fine. That is what we call as a meniscus. Right. Now, a liquid surface will always be trying to decrease its area. It will be exerting force wherever the liquid surface is in contact with something else, it will be exerting force by means of surface tension. So here, when this liquid surface, just a moment, wherever the liquid surface is in contact with the tube, okay, it's in contact with the tube over a circular region, okay, fine, over a circle. Wherever it is in contact, it will be exerting forces on the tube. The tube will also exert force on the liquid surface. As a result, what will happen? Every element of the edge of this liquid surface will be experiencing a force due to surface tension. Small force, dF. Okay. Here also, along the tangential direction, there will be a force due to surface tension acting. On every element it will be acting. We can only show on a few of them. Okay, this middle vector that I have drawn is actually tilted backwards. Okay, like towards the direction behind your screen. And this one that I'm drawing here is actually tilted forward towards the direction in front of your screen. And like that, every element of that boundary will be experiencing forces like this. Okay, because the liquid naturally has a tendency to decrease its surface area. So due to surface tension, the liquid will be pulling the molecules of the tube. As a reaction, the molecules of the tube will be pulling the liquid surface like this. Okay, so each of these forces dF are equal to TdL, surface tension multiplied with the length of the element. And at what angle do they act? They act at the angle which is equal to the contact angle between the liquid and the tube, theta. So all these dFs will be acting at the same angle theta with the vertical. Hope you all are able to visualize. Tube is a vertical tube. The dF vectors are all at an angle theta. So they will all be making the same angle theta with the vertical. Is this visualization clear to both of you? Any doubts in this? Okay. As a result of these forces, the liquid surface will get pulled up. Okay. So the liquid inside the tube will not be of the same level as the liquid outside the tube. It will relatively be higher because there are forces pulling that liquid up. Now you may ask, sir, what about liquid outside the tube? That also will have to maintain the same contact angle. There also it will be getting pulled. No. Yes. Outside the tube also the liquid will be getting pulled up, but it won't rise up significantly. We'll discuss why. Okay. So due to the forces arising due to surface tension, okay, on the meniscus will get pulled up. So as a result, liquid level inside the tube will be higher than liquid level outside. Now, force due to surface tension is a limited force. Due to that force, the surface gets pulled up. That's fine. As the surface gets pulled up, water will start rising up inside that column, okay, inside that tube. Now, this force, the force due to surface tension, has to support this extra weight. And since the force due to surface tension is limited, the weight that it can support is also limited. Therefore, the liquid will rise up to a certain height and settle there. It can't keep on going up just because there is a force pulling it up. Okay. The force pulling it up is of limited magnitude. So the height to which the liquid rises also will be limited. That height, the expression for that height is what we will be deriving now. Okay. Can one of you tell me what will be the direction of resultant of all these forces due to surface tension on the surface? Just the direction of resultant.
Upward, sir.
Upward. Correct. So the total force due to surface tension on the meniscus is acting in the upward direction. Let's call it Fy. Okay, we need to derive an expression for it first. We know dF is TdL, but the force in the y direction is not the integral of all the df's. You have to integrate the y component of df. Now, every small force df makes the same angle theta with the tube, which is vertical. Therefore, the y component of every small force will be df cos theta. Therefore, total force in the y direction due to surface tension will be integral df cos theta. Theta is the contact angle, which is fixed. So cos theta is constant. Df is TdL. So integral of that will become TdL cos theta. Okay, integral TdL cos theta. Okay, surface tension and theta are constant. So T cos theta multiplied with integral dl. What was dl? Dl is the length of a small element on that boundary. You add the lengths of all small elements of that boundary, you get the total length of that circular boundary. And the total length of that circular boundary is nothing but 2 pi multiplied with the radius of the tube. Let capital R, yeah, let capital R be the radius of the tube. Okay. This radius is what we are taking as capital R. Then integral dl will become 2 pi capital R. So the total force in the upward direction due to surface tension is 2 pi R T cos theta. Fine. Due to this force, the liquid surface will start getting pulled up. The meniscus will start getting pulled up. But as the meniscus gets pulled up, the force due to surface tension, it will have to balance the weight of the liquid that rises inside that tube compared to outside. Fine. How do you write an expression for that weight? Weight is basically density into volume into G. Density into volume. Volume is cross-sectional area pi r square into h multiplied with G. That's the weight of liquid, which is above the, or weight of liquid inside the tube, which is above the weight liquid which is outside the tube. Fine. So rho into pi r square h into G. So this force has to balance that weight. Rho pi r square h G. That's all. You get the expression for height of capillary rise as 2t cos theta divided by rho r G. This is the expression for height of capillary rise in a tube of circular cross section. Okay, hope the derivation is clear to you. You just have to visualize those forces due to surface tension acting at an angle equal to the contact angle. The resultant of all those forces will pull the liquid up. Okay, and as it pulls up, it will have to support the weight of the overhanging liquid. So as a result, it will rise up to a certain height and settle there. That height is 2t cos theta by rho rg. Okay. Now you observe this expression. The height of capillary rise means the height to which liquid rises in the capillary tube. Capillary tube means narrow tube. Okay. The diameter actually will be a few millimeters only. Fine. You can observe this in real life also. You can take some very narrow straws and try this. And in fact, water transport in plants. See, plants take in water from the roots, but it has to be sent to the stems and all also. So that water transport inside plants happens through capillary rise only, happens by means of capillary rise itself. Okay. There are narrow channels for water to rise up inside the stem of the plant. Right. So Observe how this height depends on the radius. Height is inversely proportional to cross-sectional radius of the tube. So smaller or narrower the radius, greater will be the height to which liquid will rise in the tube. And that is what you see in this picture. Okay. The last tube has the narrowest radius. Okay. Or the least radius. And in that you see the greatest height to which water rises. Okay. Now in this case, in this particular diagram, we can say the normal height is this. Okay. That extra height is what you call as height of capillary rise. Fine. In all the tubes, had they been broad enough, the liquid would have settled to this level. Okay. Over that, what is the extra height? That is what you call as height of capillary rise. Okay. Now we took the case where contact angle is less than 90 degrees. If contact angle is less than 90 degrees, the meniscus will be concave and the liquid will get pulled up. What if the contact angle had been more than 90 degrees? If contact angle is more than 90, the situation will be like this. Okay. And the forces due to surface tension, they will act this way, downward. Okay. And liquid level inside the tube will be less than liquid level outside the tube. We call that as capillary dip. Fine. So it all depends on contact angle, whether it is acute or obtuse. Fine. And you can use the same formula, H is equal to 2t cos theta by rho rg, to derive capillary dip also. Okay. If theta is less than 90 degrees, means theta is acute, this height will be positive. If theta is greater than 90 degrees, cos angle greater than 90 becomes negative. You get height negative. So using the same formula, you can calculate capillary dip as well. Okay. But remember, there are a lot of other factors also, which usually they don't explain in the books, but let's consider all those other factors. Uh, Observe that this is an open tube. Tube is open at both the ends. Okay. So the upper end of the tube, just outside the meniscus, the pressure is atmospheric pressure. Now at this level, the pressure is atmospheric pressure. Once the liquid settles to a certain height, at this height inside the tube also, the pressure will be atmospheric pressure itself. So if you observe the liquid column that is suspended inside the tube, okay, consider the liquid column that is suspended inside the tube. There is atmospheric pressure above it. There is atmospheric pressure below it. So from above, there will be P naught into pi r square force acting on it. From below also, there will be P naught into pi r square acting on it due to pressure. Okay. In addition, that overhanging liquid's weight will be acting. Okay. That suspended liquid's weight will be acting, which is rho into pi r square h into g. And this force due to surface tension will be acting, which is basically 2 pi r t cos theta. Okay. Under the influence of all these forces, it is in equilibrium. Now, if they want to twist the question, they can. They may give you a closed capillary tube where there is vacuum here. Okay. Or maybe some other pressure. So you need to understand how to write the equilibrium equation. Based on pressure above the suspended liquid, you write force from above. Based on pressure below, you write force from below. Then its weight will be there and the force due to surface tension will be there. Balancing all these forces, you get the height of capillary rise. Okay. So in a closed tube, the capillary rise may not happen to this much extent. Fine. It depends. It depends on how much pressure you maintain at the top. Okay. Now here we considered a circular cross section. Okay. Hope the derivation is clear to all of you. You have to visualize the meniscus, forces acting on the boundary of that meniscus, force due to surface tension on the boundary of that meniscus. Based on that, you derive the expression for height of capillary rise. Okay. Now I want you all to like derive height of capillary rise in case of tube having square cross section of side A. Okay. Surface tension is T itself. Density is rho. Okay. Derive capillary rise or height of capillary rise in case of a tube having square cross section of side A. Try this, both of you. In case the cross section is a square, the liquid surface, I mean the meniscus, would look like this. It will still be making the same contact angle. Okay, contact angle is a property of the liquid and the solid with which it is in contact, so that will not change. Try. Right. If you visualize the free surface, the meniscus, in this case, it kind of looks like this. Fine. And there will be forces due to surface tension acting in a direction tangential to the surface. Okay, let's say the meniscus goes like this. Okay, it's hard to show in the diagram. At every point of the surface, forces due to surface tension will be acting like this. Okay. Now each force is TDL and they'll all be acting at an angle cos the I mean at an angle theta with the vertical. So y component is TDL cos theta and integral DL will now be the total length of the boundary, which is 4a. Boundary of the square is 4a. So force due to surface tension this time becomes 4a t cos theta. In case of a circle, it was 2 pi r t cos theta because the boundary of the circle is 2 pi r. Length of the boundary is 2 pi r. In case of square, it is 4a. So 4a t cos theta. And this is the force due to surface tension which acts in the upward direction. It should balance the weight of the suspended liquid. Okay. How do you write weight of the suspended liquid? Density into volume. Volume is area of cross section multiplied with height of capillary rise. Multiply that with g, that becomes weight. That's all. Equate these two. You get height of capillary rise in this case as 4t cos theta by rho ag. So you can derive the expression for height of capillary rise for any kind of cross section. Okay, they can give you triangular cross section, rectangular cross section. Concept is the same. Okay, if theta is acute, it will be a rise. If theta is obtuse, it will be dip. Okay, now see if the tube is long enough, the liquid will rise to that height and settle there. Let's solve some problems based on this also. Just a moment. We know that pressure just outside the meniscus is P naught. And ever since we started talking about excess pressure, we have been discussing for a flexible membrane, the concave side is always at higher pressure. Now, pressure outside the meniscus is P naught. Fine. Then pressure just inside the meniscus should be less than P naught. This pressure will be less than P naught. Fine. We can even derive how much that pressure is. See, look at the left side diagram. The pressure here is P naught again. And the suspended liquid in that tube is a static liquid. And in static liquids, you can apply P is P naught plus rho GH or P naught minus rho GH. So if the pressure at the base is P naught, okay, at the same level as the surrounding liquid, then the pressure here just inside the meniscus will be P naught minus rho G H, where H is the height of capillary rise. Okay, so you can tell pressure just inside the meniscus also. And how much will that be? P naught minus pressure just inside the meniscus is P naught minus. See, this is a circular cross section. Okay, the common capillary tube that I'm considering. We know H is 2t cos theta by rho rg. Fine. If you send rho and g that side, you will be left with 2t cos theta by r. So rho g H is basically 2t cos theta divided by capital R, where capital R is the radius of curvature of the tube. Fine. Now, what have we just found out? We found out pressure inside the meniscus, P. We know pressure outside the meniscus. We know pressure inside the meniscus, means we know pressure difference across the meniscus. Can one of you tell me, using pressure difference across a membrane or a surface, what can be calculated? Using pressure difference across a liquid surface, what can be calculated? What can we calculate using excess pressure? Or what is the formula for excess pressure across a single surface? Anyone?
2T.
2T by R. We can calculate the radius of curvature of that surface. What I mean by that is we can calculate the radius of curvature of this meniscus. The meniscus can be assumed to be a part of a sphere like this. The radius of curvature of the meniscus need not be the same as the radius of the tube. Fine. What I mean is, see the edges of the tube, if you take the side view, they will look like lines. So assume this is one edge of the tube. This is the other edge of the tube. Fine. Half the distance between the edges is what you call as radius of the tube. That is fixed. But the meniscus radius need not be equal to radius of the tube. The meniscus may be relatively flat like this. Okay. That means it belongs to a large sphere like this, whose radius is definitely not equal to the radius of the tube. The meniscus may be slightly more curved, in which case its radius of curvature will be much smaller, but not smaller than the tube's radius. Okay. It's also possible in some cases that the radius of curvature of the meniscus is equal to the radius of the tube itself. It cannot be smaller than that. Fine. So by knowing the pressure difference across the meniscus, okay, pressure outside and pressure inside, subtract them, you will know the pressure difference. The excess pressure is basically pressure outside minus pressure inside. That becomes 2T cos theta divided by capital R. This is excess pressure across the meniscus, and the meniscus is one liquid surface. So you can write this as 2T by small r, where small r is the radius of that liquid surface. Therefore, you get small r is equal to capital R divided by cos theta. You can even tell the radius of curvature of the meniscus. Okay, and this can be done by simple geometry also. You don't have to apply this much physics. Okay. The angle made by the meniscus with the tube will be the contact angle. So we know that this angle is theta. Fine. Now you can see the meniscus imagined as part of a sphere. Radius of curvature of the meniscus, small r, is basically the radius of this sphere. This is small r. This is what we call as radius of curvature of the meniscus. Okay. Now we know radius of curvature of the tube, which is basically this radius, capital R. Now if this angle is theta, this will be 90 minus theta. This will again be theta. So from this triangle itself, right angle triangle itself, you can tell that small r cos theta is equal to capital R. Or small r, which is the radius of curvature of meniscus, will be capital R divided by cos theta. Okay. See, this is valid assuming the meniscus to be part of a spherical surface. Now, it's not necessary that every meniscus will be part of a spherical surface, but if the tube is narrow, you can approximate it to be part of a sphere. If the tube is quite wide, okay, it kind of looks like this. If the tube is very wide, no, the meniscus will get stretched. It won't look like part of a sphere at all. In that case, obviously, you won't be able to use this formula for radius of curvature of meniscus. Okay, so assuming the meniscus is part of a spherical surface, you can do this. Fine. Now tell me, what will happen if we make a hole in the capillary tube where the liquid is suspended? Like suppose you make a hole here. Will liquid flow out of the hole or will air flow into the hole? Correct. Okay. Air will flow into the tube. Why does that happen? See, it depends on which fluid is at higher pressure basically. The liquid inside the capillary tube is at a pressure less than P naught. Air outside the capillary tube is at pressure P naught. Air is at higher pressure than the liquid inside. So the first thing you see happening will be air going inside. After that, the liquid will start flowing out. Okay, fine. Next, see if the tube is long enough, if the capillary tube is long enough and it is circular in cross section, then the height to which the liquid rises in the tube is 2T cos theta divided by rho Rg and it settles there. Okay, rho capital Rg. where capillary is the radius of curvature of the tube. It would like to rise up to this much height. Okay. But what if the tube is not this long? What if the capillary tube is not this long? Think about it. Suppose this height is less than 2t cos theta by rho rg. What will happen? Will liquid not rise at all? Or will it rise to the top and settle there? Or will it overflow? What do you think? These are the three possibilities. Which of these do you think will happen? Give your answers, both of you. Fine. I got two answers as rises to the top and settles. Why? Vanilla, how do you explain your answer, or is it just a guess? Fine. The answer is that it will rise only till the top. It will not overflow, and not rising is not possible anyway. Okay. We have considered a liquid whose contact angle is less than 90 degrees with the tube. It will definitely rise, and it will rise only till the top. Why does it not overflow? Any guesses, anyone? I'll draw one diagram by then. Try to explain why it does not overflow. Any answer? Okay, listen. Assume these are the walls of the tube. I have shown the walls quite thick. And at the top, the walls of the tube will be rounded off like this. Fine. Of course, it will be a round tube. Fine. Somewhat kind of a swimming tube, half of a swimming tube at the top. It's like that. Okay. Imagine the liquid surface slowly rising up. Assume this liquid has a contact angle of 30 degrees. Okay, this doesn't look like 30. Let's say 60 degrees. Or fine, just a moment, I'll adjust this. Let's say the liquid in the tube has a contact angle 30 degrees with the tube. Right. Now, the tube is basically vertical. So what happens is the forces due to surface tension, no, they'll all be acting at an angle 30 degrees with the vertical, and their vertical component is what pulls the meniscus up. It is what pulls the liquid up altogether. Okay, that's fine. But imagine this meniscus reaching the top. When the meniscus reaches the edge of the tube at the top, the edges will be curving outwards like this. The tube is no longer vertical. The edges of the tube curve outwards like this. Now, when the tube is vertical and the liquid maintains an angle of 30 degrees, it will be like this. Fine. But when the tube curves outwards and the liquid maintains an angle 30 degrees with it, it becomes like this. It becomes flatter at the top. This will be the situation. Okay, let me just adjust this. Fine. 30 degrees. See, making 30 degrees with a vertical line gives you a greater y component. Okay. But making 30 degrees with a tilted line doesn't give you that much y component. That's the situation. So when the meniscus reaches The forces due to surface tension, what will happen? These TDL forces that are there, they'll be acting at a larger angle with the vertical. As a result, what will happen? Their vertical components will decrease. Initially, they'll be higher. Okay. That TDL cos theta, it will be making theta with the vertical. They'll have a significant component. But now the angle made with the vertical is greater because the surface has curved outwards. The contact angle has to be maintained the same. It has to be 30 degrees everywhere. Okay. Contact angle depends on the properties of the liquid and the solid. So as a result, what will happen? The surface of the meniscus, which was bowl shaped, tends to become flatter. Okay. So the y component of these forces which are pulling the surface up will decrease and they won't be able to lift the liquid up anymore. So the liquid will rise to the top and it will settle there. Fine. So overflow will not happen. Not rising also will not happen. It will rise to the top of the tube and settle there. So you can explain that in terms of shape of the tube. Okay. What else do you need to know in capillary rise? If the tube is closed, those cases are slightly tricky. Those we will discuss in thermodynamics actually. There you will have to apply P1 V1 equal to P2 V2, depending on how much the liquid rises. What happens to pressure in this space? You should be able to tell. Okay. Then you can tell to what height the liquid will rise in the capillary tube. Fine. So I think this much is enough about capillary rise. Solve some problems based on it. And tomorrow's class, we will discuss viscosity. If possible, we'll try to finish off this chapter, or maybe tomorrow, day after tomorrow, two classes will finish this chapter. Okay. Thank you all. We'll continue tomorrow.